Hello. So in this video, we are continuing our work with simultaneous equations, and in this video, we're going to start to look at interpreting simultaneous equations graphically. So if we plot the equations, because simultaneous equations are two of them, right? If you put them both on a graph, what does that solution look like? And you would have seen this at GCSE. But let's say if we have oh, horrible sketch, a line here and then a curve, a quadratic curve like this. Remember, this will correspond to, for example, x squared. I don't know. Minus 4x plus 6. So y is equal to x squared minus 4x plus 6. I don't know. That's just a rough, right? A rough quadratic, right? It might not be the same. It probably won't be the same quadratic as sketched, right? But then also the line y, say for example, is minus x uh, plus 3 or something like that, right? So these equations represent the quadratic and the line graph, right? Now these are simultaneous equations, right? Because they have two variables, right, on both of them, and we can solve them by substitution. So look at how we solved them last time, to get the actual solutions, right? However, that solution, also, if we plot these on the graph, the solution to these two equations actually are when the curves intersect. So this point and this point, if we were to solve it again, that's probably not the same graphs, right? I've just kind of plucked these equations out for now. But say this was the quadratic, right, and the line. Those two solutions that I've circled, that is where the pair of solutions would be, right, if we were to solve it by substitution, which we looked at last section. And so if we looked at the coordinates, right, of these two points, right, that would be the same as the solutions, right? So all in all, if we were to plot the two equations as a graph, when the two equations intersect across each other on the graph, that is also the solution to the simultaneous equations, right? Which means if we had a more complicated simultaneous equations that we couldn't quite solve, right? So say, for example, if we had y is cos x, and y is x, right? Solving cos x is equals to x is actually you can't solve that precisely. You have to look at numerical methods, meaning you have to get an approximate solution, basically. Um, so we can't solve it exactly. However, we know what these graphs look like. Y is equal to cos x and y is x. Those two graphs are quite nice to plot. And so if we were to plot them, and then when they cross over, we can kind of see visually quite quickly where the solutions would be. So it is quite helpful to consider the graphs, right? But yeah, so I'll have a look at an example then. So it says example 4, on the same axis, draw the graphs of 2x plus 3y is 8, 3x minus y is 23. So hopefully you recognize that these are line graphs, these are straight lines, right? So first of all, we have 2x plus 3y is 8, and okay, here I've drawn an axis of x and y. So to draw straight lines, hopefully you would have done that. Remember that, JCC. The best way, I think probably the best way is actually just pick 2 points, find any 2 points on the line, and then plot that, and then draw the line between them. So let's find 2 points. So to do that, just substitute any value, right, of x and y. Um, so firstly, I'm going to choose y0. Um, as I guess that's a simple example, because then x would be, if I get y0, that would go away to 0. So 2x is equal to 8, therefore x would be 4. Okay, so that's 1 point, so I can write that as 4, 0. Another point, um, let's think. Let's pick y2. I'm not going to do y1 because You could do, but then that would 3y would be 3, and then 2x would equal 5. So then x would be 2.5. I guess so. Yeah, let's do that then. Y is 1. I thought it'd be a nasty fraction. So y is 1, x would be 2.5. Okay. I was going to do y is 2, because then if y was 2 here, then 3y would be 6. Then 2x would equal to 2. 8 minus 6 is 2. Then x is 1. I'll write that here. So y 2, x is 1. So that'd be the coordinate 2.5 and 1. And 1, 2. So all I've done there is for the first equation, which is a straight line, I just found 2 points. Well, I found 3. I found an extra one. But I found any given 2 points by substituting quite numbers in, quite nice numbers, to find 2 points. Because then what I'm going to do is to sketch the graph. Remember from GCSE, let's pick these 2 points. So 4, 0, first of all. So 4 along the x-axis would be here, and then and 0 for the y, but that's just going to be there, right? 4, 0, that's 1 point. Then I'm going to pick 1, 2, okay, as it's a nice whole number. Well, x is 1 here, and y is 2 would give us this point here, okay. Okay, then what I'm going to do I'm just going to then to draw the line. I can just draw using a ruler. And by the way, I'm doing this neatly because it says draw, okay, not sketch. They don't ask this in the exam, not that I've seen in the A level, but for all intents and purposes, for this example to illustrate what's going on, we are asked to draw it. So that means you need to be exact or quite precise with the numbers, which means you need to use a nice ruler and plot your points exactly using a graphing paper. Anyway, so we've got these 2 points. So to draw the line, I can just draw the line connecting the 2 points, and I can match them up using a ruler. So I need to make sure it passes through 2 of the points that I've circled. There we are, right? That's good enough-ish. Hang on. I'm probably going to a tad bit pedantic here. There we are. I think that should be good enough, right? So now, literally draw this line, right? So connect the 2 points. Uh, there we are. So that's our line. So that'd be the line 2x plus 3y equals 8. And we will look more about straight lines in a further chapter. But for now, just need to plot them. Okay, so that's one line. Then I'm going to look at the other line here. So we've got the other equation, 3x minus y equals 23. Okay. Well, I need to plot that line, so I'm going to do the same approach. However you plot your straight lines, if you try to find the gradient of the ones, that's completely fine. However you do it, I think the best way is to just find 2 points, like I'm doing. Just substitute any numbers in to get 2 points and connect them together. So then I'm going to do, well, x is 0. Then y, well, minus y would be 23, so y would be minus 23. So I have to give the point 0 minus 23. I'm then going to say x is 1. Then y would be the 3x would be 3. So move that to the other side. Minus y would be 20. So that means y would be minus 20. So that's the point 0 minus 20. Okay. The problem is, with this particular graph, I've not drawn it to go that far down, right? So y goes down to 1, 2, 3, 4, 5, 6. It goes down to about 10 here, not 20 or 23. So what I can do instead is find points close to 20, well, points that give me 23. If I sub in x, 3x would be close to 23, right? So I could use these points if you want to extend your axis, that's fine. But I'm going to then pick a larger value of x. So multiples of 3, right? That's close to 23. I'm thinking 7. 3 times 7 would be 23. So that's quite close, which means it'll be on this axis, right? So we have small numbers for x and y. Anyway, I'm going to pick x is 7, say. Then y, well, 3x, 3 times 7 would be 21. Then 21, so that would be minus y would be 2. Okay, if we move to 21 to the other side. So minus y would be 2, which means y will be minus 2. So that would give the point 7 minus 2, which is a lot smaller than these 2 points, right? 20 and 23. So I can plot that nicely. Okay, and then I'm going to sub in x is 8, right? The next number on. So when x is 8, 3x would be 24. 24. So that means minus y would be minus 1. Okay, so that means y would be equal to positive 1. Okay, so that would give the point 8, 1. So I've got 2 points. I can now draw that on the graph. So where x is 7 is 1, 5 here. And then minus 2 would be there. Then 8, 1. But 8, so it's going to be up there. So then again, I can draw the line connecting those 2 points are circled. I forgot. Oh, I was dreading doing this topic. I really was. Exactly because of technical issues like this. There we go. Oh god. Okay. Okay. There we are. Back to normal. So let's rotate this ruler. I'm going to line it up to go through the 2 points. Uh, uh, there we are. Routes. Okay. So I'm going to draw the line there. There we are. Connecting those 2 points. Okay. And then that will give me the line 3x. Minus y is 23. Cool. So then that's part A. So on the same axis, draw those 2 graphs. Part B, use your graph to write down the solution to the simultaneous equations. Again, these are simultaneous equations. 2 equations with 2 unknowns, x and y, right? So as we discussed, the solutions would be where they intersect or cross, which is this point here. And actually, it's the point I've circled, coincidentally. That point, then, if you then read off by the axis, right, it'd be 7 on x, so x would be 7. I'll do that here. X would be 7, and y would be minus 2. Cool. Hopefully you can see that, right? That's where they cross over, and I've just read off the values of x and y. And there we are. So that's your solution, right? Without having to solve it manually, um, you can get the solution to simultaneous equations that way. So that is your solution. X 7, y is minus 2. Cool. Again, you can verify it by substituting your values into the equation, so that makes sense. But obviously there will always be a bit of leeway if you are asked to draw a graph. By nature, humans aren't perfect with stuff like that. So there will be a bit of leeway, but that should be the solution, right? If you draw your graph. Cool. Okay, so that's that question. We're going to continue on with this, and it says now on the same axis, draw the graphs of 2x plus y is 3 and y is x squared minus 3x plus 1. Okay, so this time got a line and a quadratic. So firstly, let's draw the line. So firstly, we have 2x plus y is 3. Again, to draw the line, I want to pick 2 points. I'm going to pick, say, x is 0. The y would simply be 3, because 2x would be 0 as well. Then x is 1, but then 2x would be 2. So then that would mean y is 1, okay, to get 3. So that would be the point 0, 3, and 1, 1. Okay, cool. But then I can just plot these points in, right, and that's a 3, not a 5. My handwriting. So I'm going to plot these points here, so on this axis, so x and y. So firstly, m and x is 0, y would be 3. That will correspond to this point here. Then when x is 1, y is 1, that will correspond to this point there. And then what I'm going to do, draw the line, connect them. Hopefully it doesn't bug out on me. There we are. So try and get it to pass through those 2 points as neatly as possible. There we are, right? Okay, I think that should be fine. There we are. So then that would be the line 2x plus y is equal to 3. Okay, now we need to sketch this quadratic. Y is x squared, let me just write the ruler here, x squared minus 3x plus 1. So with quadratics, obviously you can't just plot points and connect them because it's not a straight line. So remember how we sketch quadratics then, think back to the last chapter. We can consider its y-intercept, which should be when x is 0. When x is 0, y would just be 1. So the y-intercept uh, would equal 0, 1, right? With y is 1. So that would be here. So we know our quadratic has to pass through there. And the turning point might help as well. So the turning point, we can complete the square, remember? So x minus a half of 3 minus 3 over 2 all squared. Then minus 9 over 4 by squaring it plus 1. Then we can simplify it to get x minus 3 over 2 all squared. Minus 9 over 4 plus 1 would be minus 1.25, okay? I'm going to leave it as a decimal because I think it's a lot easier to interpret, right? So therefore the turning point, right, would be when for x value you have the bracket has to be 0, so x has to be 1.5, which is 3 over 2, to get the bracket 0, and then minus 1.25. So if we read that off the graph, 1.25 is there, minus 1.25 would be about there. So that would be where the turning point would have to be, right? Okay. Okay. So we've got the key information. We could find the roots, but I'm gonna just find some more points, right, to actually get like a really good idea of where the graph would go, the quadratic, because we are drawing it. So we do need to be a little bit more accurate. So that's a turning point. That'll help. You can find the roots, but the thing is they're quite nasty roots. So it's up to you. But instead, I'm just going to find some nice points to consider. So, like with before, let's say well, we consider when x is 1.5. What happens when x is 2, right? When x is 2, where should we do it? Here? No, here. When x is 2, y would be what? Well, I'm going to substitute 2 into here, the quadratic, right? So 2 will be 2 squared, 4, 4 minus 6, right? Which would be minus 2 plus 1, that'd be minus 1. And actually, well, there we are. It would actually be coinciding with that point on the line there. Okay. Then x is 3, for instance. Then y would be, well, 3 squared would be 9. And then 9 take away 9, which should be 0 plus 1, so y would be 1. So when x is 3, y is 1, so it would be, have to go through there. Okay, and that's probably enough, probably. But then let's consider the negative side, right? So then when x is, well, we considered x is 0, let's consider x is minus 1. Because 0 is the y-intercept, right? So y would be minus 1 squared, that'd be positive 1. 1, okay, minus 3 times minus 1 would be plus positive 3. So 1 plus 3 is 4, plus another 1 is 5. So if we plot that, 1, it'll be there, and actually it'll correspond to that point in the line as well. Um, so actually, I think I might be good. Actually, I've got the general gist. So the turning point, remember, is there. So it would have to look like that, right? Something vaguely like that, right? So there we are. We sketched it on the same graph. Use the points to aid us to sketch it. Okay, it's a bit wobbly there, but I'll live. Okay. So yeah, so that's how you draw it. Okay, it's a bit different to sketching because sketching all we need is the key details of what the wind-sept is, what the turning point is if it's quadratic, what the roots are, and the general shape. That'll be fine as long as you've got the key information. With drawing, you need to be a little bit more precise in exactly where the points go. So notice here, I plotted these points on, and then I made sure the graph pretty much goes through those points. So it's more of an accurate sketch, right? Because we're drawing it, which is a key command word there. So I've got some points to actually go through to make sure it's a proper sketch, right? Right, it's more than a sketch, it's a drawing. Okay, so that's where it goes from. Then it says for part B, use your graph to write down the solutions in this case, which is again why we draw in the graph because we want to get some accurate solutions, which comes from again if when they intersect. So it's going to be this point there, right, and this point up here. That's where they cross. Okay, let's deal with this point first, point 1. Well, that's going to be this point here when x is 2, isn't it? So x is 2, then the y value is -1, right? Again, if you read off the graph there, you get x is 2, y is -1. Then the next solution would be up here, right? So if you read off that graph, it's going to be when x is -1, and then y would be up here, which should be 1, 2, 5 there, right? And that's your other solution, okay? And there we are. Those are the two solutions, right? Cool. And there are two pairs, because obviously when we solve quadratic simultaneous equations, you can get two different pairs of solutions, unlike linear ones. So there we are. So there we are. So that's another way we can solve simultaneous equations. Now, obviously, not a good method all the time. It depends. Like I said, it's good if you kind of want to see roughly where the solution is, or again, if you have really difficult equations to solve, like when we looked at the start with cos x and x, but you can sketch them. Okay, so if you can sketch them, see where they cross over, then you can get quite a good feel for what the solution is, even if you can't solve it properly. You know, but that's the idea of this, right? Is to sketch these the graphs because um, sometimes, right, you can rearrange the equations to make them graphs. So, for example, this one, 2x plus y is 3, we can also say y is minus 2x plus 3, which hopefully you can recognise as a straight line. So that's essentially what we're doing. All we're doing is plotting these two curves, right, these two graphs. Then when they cross over, they have the same solution, which corresponds to the solution to the simultaneous equations. Okay, hopefully that should be a familiar concept though, is the idea that when graphs cross over, that's the solution to their simultaneous equations. Okay, cool. Okay, but we can use the idea to help us if we have this in our mind about graphically when the graphs cross over, that's when that's when they intersect, that's when the solution occurs. We can end up solving more complicated questions as well, like this one. So for in this example, we are told the line with equation y is 2x plus 1 meets the curve with this equation at exactly 1 point. So I'm going to write these equations down. So y is 2x plus 1 and kx squared plus 2y plus k minus 2 equals 0. And we are told that they meet at exactly 1 point. Okay. Well, this is quadratic simultaneous equations, isn't it, at the end of the day? Really, because I can substitute y into here, and then I can get an equation for x. So I'm going to do that then. So if I call this equation 1 and equation 2, I'm going to say sub y into 2, not into 1, because y is equation 1. That wouldn't help me if I substitute it back in. So substitute it to the other equation then to get kx squared plus 2y, so 2 lots of x, 2x plus 1 plus k minus 2 equals 0. Then I can expand this and see what I can do with that. So kx squared plus 4x plus 2 plus k minus 2 equals 0. And then I can tidy this up to get kx squared plus 4x. 2 minus 2 would go away, so you just left plus k equals 0. Okay, there's nothing more we can do there, but we are told the line, this line, and this curve, which is shown by this, they cross over at one point, okay? And we have a quadratic. So what that means is if they cross over at one point, say it's going to look like this, right? So you have the quadratic here, because this is a quadratic, right? I hope you can see that. And then the line will intersect at one point only. Say, for example, like there, just a generic line and quadratic graph, not meant to look like this. Just a generic example. It's going to cross at one point there, somewhere there. So that's what that means graphically. But what does that mean in reality? Well, there's only one solution to simultaneous equations, and we discussed this last time. And there's only one solution to a quadratic simultaneous equations. That means the resulting quadratic that we get here has to have a discriminant of 0 because the roots have to be. There's only one root really, one distinct root. So as one point. What did I say? One point of intersection, was it? Uh, one point of intersection, yeah. That means the discriminant here, b squared minus 4ac, has to equal 0 to give only one distinct solution because there's only one point of intersection. Okay, so then let's just deal with the discriminant because then that'll help us find k. So b squared would be 4 squared, that'd be 16. Minus 4 lots of a, which would be k. Lots of another k, which would be k. Lots of c, which would be k as well, equals 0. Then I can expand this to get 16 minus 4k squared equals 0. Then I can say 4k squared equals 16 by rearranging, by adding 4k to both sides. Then k squared divided by 4 will get 4. Then k would be plus or minus root 4, which would be 2. So those are two solutions for k, right? Uh, okay, but it says here for part A, find the value. Again, it's singular, so it means only one value. But how do we work that out? Because we've got two values. Well, let's look at the question. It says that k is a positive constant. Okay, so it has to be positive, so it has to be the positive answer. You can't have a negative. So as k is positive, that means the only solution is k equals positive 2. Only, so that's our value for k. Cool. Okay. Then it says for this value of k, find the coordinates of the point of intersection. Okay. So at that point we need to solve, right? So remember that graphically, if two curves cross together, that solution is the same as the solution to simultaneous equations. So to find the point of intersection, it's the same as solving the simultaneous equations, right? So that's what we're going to do. So we solve the simultaneous equations. Well, we're going to just solve this quadratic then, because that's what we need to do. So we found what k is, so then we can say the quadratic would be 2x squared, because kx squared would be 2x squared, plus 4x plus k. Now k is 2, that equals 0. I'm going to divide by 2, just because I don't like the number in front of the x squared, to then get x squared plus 2x plus 1 equals 0. Can we factorise? Maybe we can. So we need to times to get 1, right? Positive 1 and add to get 2. So just what 1 and 1, right? Because the factors of 1 are itself 1 and 1. And I can add these two together, right? To get positive 2. So that'd be a factor, right? X plus 1 equals 0. So then, really, if you set each bracket equals 0, the brackets are the same. So the only solution gets x is minus 1 in this case, which makes sense, right? Because it only says there's only one solution, one point of intersection. So we only expect one value of x, right? Which is what we've got here. And remember, again, this is called a repeated root, or we call it equal roots, okay? Because of the fact we kind of got two factors, right? Because of how we factorise. However, they're both the same. So it's x plus 1 squared, if you will. that's repeated because it's itself twice, right? It's the same factor twice, so it's the same root twice. So they're equal roots because you get x minus 1 twice, but they're both x minus 1, so they're the same. So you only get one distinct root, even though they're equal. So we say there's only one distinct root, which again, remember, is why we set the discriminant equal to 0. Anyway, so that's x minus 1. That's what we get to solve. But then to solve the point of intersection, we need a y value as well. So we need to find the y value. Well, luckily, we know how to write y in terms of x. So if y then is 2x minus 1, which comes from the first equation, right? 2x plus 1, sorry, from the first equation. Then y, when x is minus 1, would be 2 lots of minus 1 plus 1. That would be minus 2, add 1, that would be minus 1. Cool. So then that's our value then. So x is 1 minus 1, y is minus 1. Okay, so that's our solution then. But it said find the coordinates of the point of intersection. So we need to, very key detail, but what we need to then say is write this as a coordinate. So it has to look like x, y, this way, right? Well, x and y minus 1, so minus 1, minus 1. So that is your final solution. Okay, that's the coordinates of the intersection. Okay, so that's really it, right? We're just applying what we did last time, essentially. Nothing really new in this regard. We looked at the example like this last time with quadratic simultaneous equations. The idea that you can use a discriminant when given how many solutions there are to work out missing information, like what the value of k is, right? Pretty classic type of example. Question I like to ask, but yeah. So nothing new there. So if you're given graphically two curves, when they cross over, it corresponds to solving their simultaneous equations. And then we know how to solve simultaneous equations. We looked at it in the first two, in the previous two sub chapters, right? So yeah. Okay, now we look at some exercise questions, and we're given this question. The line with equation 4x minus 1 does not meet the curve with this equation. X squared plus 2x plus y squared is k. Find the range of possible values of k. Okay, well, again, we've got simultaneous equations. So y is 4x minus 1, and x squared plus 2x plus y squared is equal to k. Call that equation 1 and 2, for instance. So, again, if we consider in their intersection, that means consider the solution to their simultaneous equations, okay? So let's solve it as normal, as if they're simultaneous, well, they are simultaneous equations. And let's do it how we normally would, right? So let's do substitution. So we have y already given us 4x minus 1, so we can substitute that in quite directly into here for y squared. If we do that, we're going to sub y into the second equation to get x squared at 2x with y squared, which is 4x minus 1, times by itself, 4x minus 1, minus k equals 0, to move the k to the other side, to make the equation equal to 0. Then I'm going to expand these brackets, we're going to move it over here, we're going to go x squared plus 2x plus 4x times 4x is 16x squared, minus 4x minus another 4x minus 8x plus 1 minus 1 times minus 1 is plus 1 minus k equals 0. Then I'm gonna tidy this up. So I have 16x squared, another x squared at 17x squared. Then I have 2x minus 8x, that'd be minus 6x. Then I have plus 1 minus k, right? And I can't simplify that anymore. And there we are. So we got this quadratic. Now again, at this point we need to, because we have k, what can we do with that? Well, they told us that this line here, so that's the first equation, right, does not meet the curve, which means it does not intersect this curve here, which is the second equation there. What that means, if they do not intersect, that means there are no roots between them, right? Well, if there's no solutions between them, that means the discriminant has to be negative, okay? So as no intersections, this time the discriminant has to be less than 0, okay? Um, So this quadratic here. So if we work that out, b squared, so minus 6 squared would be 36, minus 4 lots of 17, lots of 1 minus k is less than 0. And we're going to get an inequality, which makes sense because it told us to find the range of values of k. A range usually implies that there's an inequality. Okay, because there can be a bunch of different values possible. Anyway, so if we solve this, right? So 36 minus 4 times 17, first of all, is 68. Of 1 minus k less than 0. Then I'm going to do it, expand that. So 36 minus 68. Minus 68 times minus k be plus 68k less than 0. Then I'm going to, we can put these two numbers together, right? So 36 minus 68 will get me minus 32 plus 68k less than 0. Then I can move the 32 to the other side. Then simply k, if I divide by 68 with 32 over 68, that would be, if you simplify that, 8 over 17. Okay, as simplified as possible. And that is your solution, right? That is the range of values of k. So there's not one single value of k. Remember inequalities, you get a range of values of k, right? So as long as k is strictly less than 8 over 17, any value of k less than that will be feasible. Okay, will be a solution to this. So that's our range of values. There we are. Cool. So again, we're just using discriminant, right? So we solve it as we normally do, nothing new there. Then when we get to the quadratic well, we can use the fact that we can consider the discriminant because of the fact that in this case, the two equations don't meet. So which means there are no solutions to the simultaneous equations. Therefore, the discriminant of the quadratic has to be less than 0. Because remember when we looked at discriminant, if the discriminant was less than 0, the quadratic, there is no solution to that equation. Okay, so that's where we get to this. So again, it's the same ideas as what's it called? As with the last time. But yeah. Okay, so let's leave off with this question. So we are told a swimmer dives into a pool. Her position, p meters underwater, can be modelled in relation to a horizontal distance. So x is the horizontal distance and p is her position underwater. Okay, and it's given by the quadratic equation. P is a half x squared minus 3x. Uh, Now they've not sketched this because there's no quadratic. We could though, I guess. But let's read the rest of the question. The position of the bottom of the pool can be modelled by the linear equation. P is a 0.3x minus 6, and that'll be probably this line here, right? Because if you imagine this as the x-axis, so that'd be 0, the origin. This will probably be minus 6, which would be the y-intercept. And the gradient is 0.3. So this is the line here, but they're not told us what the quadratic would be. Now, the quadratics are positive, right? So it could have this sort of shape, right? So we could go there, or it could go below, or it could indeed go underneath. What we're trying to work out is whether this curve, this quadratic here, given by this equation, does it ever touch or go underneath this line here, which represents uh, this, right? So hopefully you recognise there's some sort of simultaneous equations going on, right? We're considering whether two different curves cross over and when they intersect. So is it going to be above the line here, this line here? Is it going to be above like this? Or like this, or is it gonna simply touch it about there, or is it indeed gonna go under like this? That's what I want to work out. But how are we gonna work that out? And that's what it says. Determine whether the model predicts the swimmer would touch the bottom of the pool, which again is this here, but it's represented by this line here, which they're drawn for us, but they're not drawing a quadratic. Obviously, if they drew the quadratic, we'd be able to just see if it would look like this, right? You can very clearly see. Okay, does it touch the bottom of the pool? There we are. But it's 5 marks, so we do need to do some work. Okay, well, we could sketch the quadratic potentially, but it's not an accurate drawing, right? It's just a little sketch. So the best way is actually probably to consider simultaneous equations. So we want to predict whether the swimmer would touch the bottom of the pool. Okay, so that's going to correspond to, if you imagine this quadratic, which again is given by this, we don't know what it looks like. We not too bothered to sketch it exactly. We want to know whether this equation has solutions with this. If it has a solution, remember, think about what we discussed at the start. If it has a solution, then the curves will cross over and intersect. If they intersect like this, for example, that would mean the swimmer has to touch the ball. It has to touch this line here. So imagine the swimmer, it basically is on the U shape, the quadratic, right? Does it touch the bottom of the pool? Which means, is there any intersections between those two graphs? Well, let's have a look. So P is a half x squared minus 3x. So let's write that one down. And P is 0.3x minus 6. Well, we want to consider the solutions, right? Whether they do intersect, right? How are we going to do that? Well, we just solve it simultaneously again. So we call that equation 1 and 2. If they intersect, that means the simultaneous equations will have a solution, right? So let's just go on with solving it. And if we can't solve it, then something will go. We'll be able to tell, right? But let's just solve it as normal. Well, we can substitute p, right? This value of p into the equation 1, right? So let's do that then. So we're going to sub p into 1. So we solve it, we just substituting like we always do with quadratic simultaneous equations. Nothing new there. So substitute p into 1. That means 0.3x minus 6, which is equal to p, right? From equation 2, has to equal half x squared minus 3x, which is equation 1. Okay. And then from there, we can just put everything to the other side to make it equal to 0. So we have a half x squared minus 3x minus 0.3x plus 6 equals 0. Then I have a half x squared, okay, minus 3.3x, right? Plus 6 equals 0. I don't like this x half, so I'm going to just times by 2 to every term. To scale the equation up to get rid of the fraction. So I'm going to have x squared, half times 2 is just 1, x squared minus 6.6, right? X 3.3 times 2 is 6.6, and then plus 12 equals 0. Okay, so that's a lot nicer to work with. Okay, now we could solve it, but can't we just consider the discriminant to really cut down our working? If we consider the discriminant, the amount of solutions, we can work out the sign of the discriminant to work out how many solutions there are. Okay, so let's work with that then. So let's consider the discriminant, which would be b squared minus 4ac, right? So we don't have to solve it, go all the way. We can just consider the discriminant. So all we're looking for is there any solutions, right? Because if there was, then the diver has to touch the pool. Anyway, so that would equal b squared minus 4ac, well, minus 6.6 all squared, minus 4 lots of 1 of positive 12. That would then equal, we put all that in the calculator, right? You get minus 4.44. Well, it's a negative, isn't it? And that's less than 0. So that means, if you think that's discriminant, what we did, if the discriminant's 0, that means there are no real solutions uh, to the equation, to the quadratic. So if that means there's no solutions to the quadratic, so there's no solutions to the simultaneous equations. So therefore, no solutions to simultaneous equations, which means that if we consider plotting these two graphs, because there's no solutions to these two equations when they cross, that means they can't cross, right? Because there's no solutions to simultaneous equations, and we discussed right at the start that when two curves cross together, they intersect, their graphs intersect. That means I have to have a solution to the simultaneous equations. Well, in this case, there are no solutions to simultaneous equations, which means there's really no intersections between the two graphs. So actually, therefore, Uh, the graphs do not cross. Right, so remember these two graphs here. This is the first one, and this is the second graph here and here, right? Which means if they don't cross, well then, well, simply, the diver's position, which is by the first equation here, the position never ever touches or crosses with this bottom of the pool here, which means the swimmer will not touch the pool. Therefore, the swimmer. There we are. Cool. So yeah, so that is why it really is helpful to actually visualize what these simultaneous equations are doing, right? Because you can, if you visualize whether they intersect, that, and then that means is there solutions to simultaneous equations, and I can work out simultaneous equations because we know how to substitute, we know how to solve quadratic and linear ones. We looked at that previously. If I know how to solve them, then I can determine whether two given graphs intersect. And in this case, there's a real life implication, right, of determining how if the swimmer touches the bottom of the pool. For example, if it did cross the bottom of the pool, maybe the pool may be too shallow. You don't want a pool that's really, really shallow, right? So that could have a lot of implications, right? But in this case, it does not touch the bottom of the pool. Okay. Um. So yeah, that's really it, right? So essentially, it's still just some terms of equations. Considering the discriminant is really helpful to consider whether there is any intersections with the graphs that were represented by these simultaneous equations. Uh, Therefore, if there is an intersection, we can solve the simultaneous equations, which means the discriminant has to be positive. On the contrary, if there are no crossing with two graphs, then there is no solution to the simultaneous equations, which means the discriminant has to be negative, like with this example here, right? They did not meet the curve, so the discriminant was negative. Okay, so I'm going to leave that there then. So see ya.